order of f of n plus order of g of n, that is equal to order of maximum of f of n comma g of n. Okay, and we have proved it, how it comes. So let us see some more properties. Another property is that is f of n is equal to order of g of n and g of n less than or equal to h of n. That implies f of n is equal to r of h of n. So this is also almost clear. Anyway, proof is not complicated, it's straight proof only. When you say this f of n is equal to r of g of n means, what you can say? You can say f of n is less than or equal to some constant multiple of g of n. So remember, this is only for derivation purpose we are writing, but don't assume this itself is a definition, because definition already we have seen that there are so many other things are there. So there exists a constant c belongs to r such, and n not belongs to n, such that this inequality will be hold good for all values of n which are greater than less. So all these things are there. So you have to assume that whenever I am writing like this, so all these factors are there. But for the derivation purpose, we are taking only the inequality because that is sufficient. Other things are assumed to be there. Okay. Here already one more inequality given, that is g of n is equal to g of n less than or equal to h of n. So we can say that this is less than or equal to c into h of n, because g of n is less than or equal to h of n, right? So if f of n, that means this implies f of n is less than or equal to this. So this means the f of n is equal to r of h of n. Okay. Then next property is any function can be written as a big O of that function. That is f of n is equal to order of, that is any function is order of itself. What do you want to say? That is any function is order of itself. So f of n is equal to order of n. So this is also trivial because we can write this f of n is less than or equal to 1 into f of n, right? So this 1 is our constant. So the inequality has come, and again we can write this. Okay. So this is another property. And one more important property is any constant if you take. So any constant that is equal to r of 1. Why? Because we can say c is less than or equal to c into 1, right? So this is our constant function. So any constant that will be equal to r of 1. So this property that is also there. So these are the some of the important properties of big O. Yeah. So like big O, there are several other notations available. So two more notations that is important for us. In the big O notation, what we have seen is f of n less than or equal to some constant multiple of g of n. So what it means? So it means that g of n is an upper bound because this is the larger factor. If you have taken f of n and g of n, so you see that g of n is larger than this. So a constant multiple. Okay, constant multiple we don't bother about it. Okay. So when you compare these two functions, this is an upper bound. So why we want the upper bound? Because if you write the algorithm and if you calculate the time and space, we have to see that what's the maximum time it is taking and what is the maximum space it takes. So we want the upper bound. So that means once you fix the upper bound, whatever the instance you are taking. So every problem, that is algorithm is developed for a particular problem. So every problem is defined over a domain. So that's very important. So what we mean by that? That is, for example, if you take multiplication of two integers, this problem already you have considered, right? Multiplication of two integers. So if you write the algorithm for multiplication of two integers, when we run the algorithm, what we can do? We can give any of the two integer as an input to that, right? So how many inputs you can give like that? How many instances? That is when you take two integers, that is one instance. So first I can take 10 and 15. So that is one instance. Then if I take 25 and 30, that is another instance. Like that, when you take two such integers, that becomes one instance. How these instances are, from where we are getting instance? That is from the set of integers, right? So we have set of integers. In the set of integers, if you take two factors a and b, two numbers a and b, and this becomes an instance, right? So that means we have written the algorithm for multiplying two integers. Therefore, for the problem, the instances are any two integers, and these instances are being derived from the set of integers. So the set of integers is called the domain. Okay, so every problem will be defined over a domain. So the domain consists of set of our instances or inputs, right? Okay. So from there we are taking. Therefore, when you have an algorithm, we may give different instances, So one instance may take maybe 5 milliseconds, another may take 10 milliseconds, something like that. Okay. So if that's the case, out of all the instances, what will be the maximum time? So if you set the upper bound for that, then any instant you take, it cannot go beyond the upper bound. So that's why we are looking at the upper bound. Okay. So and the big O notation that defines the upper bound. So that's what you have to be very clear about it. Because later on when we say that how this notation is associated with the practical implementation of a particular algorithm. Okay. So that you have to remember. Okay, now like big O, I mean, there are several other notations available. Another important notation that we will also use in our course. So that is big omega notation. Okay, big omega. So big omega, so once again the definition is almost similar, except one change. Let me write the definition. So we can take that let f comma g are the g be the two functions from set of natural numbers to set of non-negative real numbers. Okay, and if you say f of n is equal to omega of g of n, then there exists constant c belongs to r, n naught belongs to n, such that this f of n is greater than or equal to c into g of n. Okay, so these factors are already we have discussed while looking at the big O notation. The same explanation, therefore I am not focusing on this because these are already been discussed. So what's the difference? The difference is only the inequality. In the big O notation, the inequality is less than or equal to. But in the big omega notation, the inequality is greater than or equal to. So that means this becomes the lower bound. Okay, so remember big O notation is being used for defining the upper bound, and big omega notation is used to represent the lower bound. So anyway, when we say something about upper bound, anyway it's clear because already I have said that every problem is defined over a domain, and from the domain only we derive the instances, and out of all the instances what will be the maximum time it takes, that gives the upper bound, right? So the upper bound having some meaning, but what do you want the lower bound? So lower bound is we say that out of all instances, it is taking the minimum time. So if it's a minimum time means whenever we are running the algorithm, it may take more that particular time or something more than that. So what is the point in defining a lower bound? So that doubt we may get it. But this is also important in the theoretical concepts. The reason is one example I can say that, as I mentioned earlier, if you take a sorting problem, there are plenty of sorting algorithms are being available. Anyway, our task is to sort the value, but people have developed so many algorithms. These developments are based on, okay, these developments are based on improvement over the time complexity or the space complexity, sometimes both. So this improvement, maybe now we have some algorithms and people are not trying for any new sorting algorithm. So why people are not trying for a new sorting algorithm now? Because we should know that it has achieved maximum optimist value. Okay. So you see, we are keep on finding, better algorithm. So for example, we take only the time factor. So we developed an algorithm for sorting. Then we are not happy with the time factor what we achieved. So we are trying to improve that. So then another person comes, he sees that okay, some more improvement possible. Anyway, he is developing another algorithm. If we go like that, how long we go? So anyway, remember that it cannot go beyond the lower bound, right? It cannot go beyond the lower bound. So once it reaches the lower bound, then the algorithm is called optimum algorithm. Then the algorithm is called optimum algorithm. So optimum, once it reaches optimum, then you cannot find any better algorithm than that. So there is no point in wasting our time. Okay, there is no point in wasting our time. For example, the sorting algorithm, the optimal time is order of n log n. Okay, order of n log n. So we can say that once you get the algorithm with n log n complexity, so that is a better algorithm. So you cannot make any improvement over that. Okay. So even if we take heap sort is taking n log n. But merge sort that is also taking n log. Maybe you'll be seeing later on. I don't know whether you have studied because anyway the theoretical complexity you won't be. Okay, anyway, the merge sort is also n log n, but the problem is the space complexity is high, and hence we are going for heap sort algorithm that takes lesser space as well as within the n log n complexity. Okay, so like that there is a factorificant development of any new algorithm. Therefore, in this case, omega is required. Okay, omega is required to define the lower bound. So if we know the lower bound, then only we can conclude that whether we have got the optimal complexity or not. Okay. So for that, theoretically, this notation is required. And one more notation that is also we commonly use. So that is called theta notation. That is called theta notation. So theta notation, once again, let me give the definition. So here also, two functions f and g from set of natural numbers to non-negative real numbers. And if we say that f of n is equal to theta of g of n, okay, then there exists two constants C1 comma C2 belongs to R. Now we are taking two constants. C1 comma C2 belongs to R. N0 belongs to N such that, okay, one more thing I forget to write here. That is for all n greater than N0. Okay, so that's also there. I missed it there. Okay, so N0 belongs to N such that. So note down this also there in the omega notation, right? Okay, so N0 belongs to N such that C1 into G of N is less than or equal to F of N less than or equal to C2 into G of N for all n greater or equal to N0. For all n greater or equal to N0. So what this inequality conveys? You see, with respect to one constant multiple, okay, with respect to one constant multiple, the g of n becomes the lower bound. And with respect to another constant multiple, this g of n is the upper bound. So a particular function is both the lower bound and upper bound. Maybe the constant factor varies, but in the asymptotic notation, we never bother about the constant factor, right? Therefore, if a function is both lower bound and upper bound, that means the function is same. So therefore, when we have to use the theta is whenever the complexity is exact. Okay, exact. It is exact in the sense that it is both lower bound and upper bound. Then in that cases, the theta notation can be used. So remember, at the later part of the course, we may use this notation frequently. Sometimes we put omega, sometimes we put theta, sometimes we put O. So that time you should not think, oh, how it comes. You should not think that way. Okay. So these notations are very important. So we put whenever we put a notation, automatically, okay, you have to see that whether it's upper bound, lower bound, or exact complexity, something like that. There are few other notations there because anyway, I don't want to confuse you. So these three notation is sufficient for this course, and those who are interested, they can learn it later, no problem. And one more thing is abuse of notation. Actually, is a notation that we are using here is not the correct one, but the clarity we are using that. So that's why sometimes people used to say that it's abuse of notation. So what we abused here, for example, if I say f of n is equal to r of g of n, this is not correct. This is not exactly correct. But for the clarity and for writing simplicity and maybe this is fine for us, but we should understand though we are writing like that, I mean what it actually is. So the correct notation is not equal to. The correct notation is belongs to. So we should say that f of n belongs to r of g of n. F of n belongs to r of g of n. Okay. So now you see, instead of writing belongs to, we are writing. So whenever we are writing equal to, you should know that it is something like belongs to. So if you say belongs to, then it may associated with the sets, and you should not confuse that. So for the clarity purpose and for derivation purpose and all, we use this. Okay, that's all. If you say this belongs to this, means this is supposed to be a set, right? This is an element. Element only belongs to a set. So if I say R of f of n, okay, something like that, R of f of n. What is R of f of n? So that means it is set of R. Okay, when we say R is a set, R is a set. So I am taking R of f of n. Okay, so this is set of all functions G from set of natural numbers to set of non-negative real numbers, such that their exit C belongs to R, N naught belongs to N, such that this G of n less than or equal to C into F of n for all n greater or equal to n naught. So now within order F, therefore here G comes to the left and F comes to the right, right? So this is the set of all values. So big O is the set of all values. Okay, so that means out of the set, it must be the one of the function. G is one of the function in the set. So that's what we have to consider. So why we say that, for example, if we have the value something like 2n. So if you have the algorithm time complexity is something like 2n. So 2n, how do we write in the big O? It's big O of n, right? We write it is big O of n. So similarly, if you have a 4n, 4n is also big O of n. Okay. So now this is one function, this is another function, something like that. So all these functions are big O of the same thing. So big O of f of n means like that. There are several functions available. The constants can vary, the n naught can vary. Okay, no problem. But it is not the one function. There is a set of all function out of which it will be the one, right? So this is what the understanding is supposed to have. Anyway, if you have any doubt, please ask now so that I can clarify. Okay, so remember the big O notation is something like a set. So this is what the correct notation, but only for the clarity and other things we are using this one. Okay, so you should not think that it is something like a value, but it is a member belongs to a set. So this understanding also very important. And as a computer scientist, wherever you go, these notations, any competitive examinations you take, some problems will be there based on these asymptotic notations. Okay, so that time if you are not clear about it, then you cannot write the correct answer. Okay, so that's why this are I am spending more time because now it's a fourth class. Still we are in the foundation. Because without foundation, if you go to the concept, it may not be good. So I am giving more clarity with more examples, okay, more explanations. But the problem is interaction from your side is very poor. Only one or two people are that too. Whenever I am asking, they are answering. But looks like I don't know whether you understood or still you are keeping quiet. Okay, so remember, if you have a doubt, you can ask immediately so that we can clear your doubt and proceed further. Okay. So can I move to the next concept?
Yes, sir.
Yes, sir.
Okay. Okay. Now we have to see some facts. So these facts are very important to solve some problems. Okay. Anyway, I am not going to give proof because if we keep on giving more details like that, unwanted details and all, maybe it's good for you, but we cannot cover the syllabus. So only the facts I am going to give you. Making use of the facts, you can solve certain problems. So first fact is when you take the limit function, limit. I think you have studied limit, right? So limit n tends to infinite, f of n by g of n, if that belongs to the positive real number, equal to 0 is not there. Okay, greater than 0, positive real number. Then what we can conclude is the function f of n belongs to. Now you see we are using belongs to. Okay, so now you understood that why I am using belongs to in some place and why I am using equal to in some places. Don't confuse that. Okay, I am using belongs to. So f of n belongs to theta of g of n. So theta notation also we have seen already. So why we take n times infinite? Because this notation is asymptotic. So when n is larger, okay, maybe even near to the infinite, what will happen? Okay, so this is asymptotic notation, and hence this n is the size of the input. And these are the functions in terms of the size of the input. For example, f of n, if you say that f is in terms of the size of the input here is n. So what we mean by the size of the input? Suppose you want to sort 10 numbers. 10 is the size of the input because 10 inputs you are given, right? So the complexity must be stated based on the size of the input. So whenever we are using the variable, you have to have a thinking that. So this is the size of the input, but you should not consider something like some arbitrary variable that we use in mathematics. So the mathematic idea we need, but at the same time we have to associate it with the algorithmic concepts. The algorithm, what it denotes. So that's what you have to observe. And based on that, you have to see the remaining thing. So here what it says is if you take the thing f of n by g of n and if you make this n tends to infinite, that is when you take larger size, larger instant size. And that time that value is some real number, positive real number, then straight away we can say that this f of n belongs to theta g of n. That means this g of n is the exact complexity. Theta means exact complexity. So this notation you can use that. Then second property is if you say limit n tends to infinite, f of n by g of n that is equal to 0. Okay, here 0 is not there, but here we are saying that when 0 comes, then you can conclude that f of n belongs to R of g of n, but g of n does not belong to R of f of n. Okay, remember that in the recorded video, sometimes the audio and video is not, matching. Okay, I think audio is coming a little earlier before the video. Okay, anyway, it's due to network issues or something like. Okay, so when you listen accordingly, because sometimes my words are coming quickly, but after few seconds only the writing part is coming. Okay, so you adjust anyway because that is not in our hand. Just we can record and give you. Okay, so if this limit value is equal to 0, then f of n belongs to R of g of n, but g of n does not belongs to R of f of n. So one function belongs to the set, another the reverse is not true. Reverse is not true. Okay. Then the third property, limit n tends to infinite, f of n by g of n is equal to plus infinite. So anyway, minus infinite it cannot go because the function itself is defined over the non-negative real number. So it goes through the positive infinite only. Yeah, but specifically we have stated that plus infinite. Positive side, the larger value. So in this case, we can say that f of n belongs to omega of g of n. Okay, now omega of g of n, but g of n does not belongs to omega of f of n. So these are these three properties. Okay, anyway, some more thing there, but anyway, this much is sufficient for you. So these properties you should know that. Why you know is anyway I can take a problem and just tell you that how we are making use this property. So for the first problem, I mean one of the problem we cannot discuss a lot. One problem I can take. So the problem is saying that the log n belongs to order of root n, but root n does not belongs to order of log n. So this you have to prove. Okay, maybe we can say prove that. Prove that log n belongs to order of root n, but root n does not belongs to order of log n. So obviously you know that something related to this, right? Some one belongs to other one does not belong to. So something like that. So you have to check that this limit value is equal to 0 or not. That's all. So what you can do? So in this case, this is our f of n, this is our g of n. F of n is log n, g of n is equal to root n. So we can take limit n tends to infinite. So log n by root n, right? So f of n by g of n. So this one we are taking f of n by g of n. So now what happens if you apply infinite? N tends to infinite, right? N is a very large quantity. So when n becomes infinite, what happens? This is log infinite, right? It's a log infinite. What's the value of log infinite? What's the value of log infinite?
It's infinite, sir.
Infinite. Why?
Sir.
Why? Because log is an increasing function. Log is an increasing function. So increasing function means when you increase that value, automatically logarithm also increases. So when n becomes infinite, automatically that logarithmic value also reaches to infinite, right? Therefore, log n is equal to infinite because log is an increasing function. Similarly, root infinite, denominator having root infinite. So what is the value of root infinite? That is also infinite because infinite is undefined. So root of undefined value is once again undefined, right? So that is also infinite. So you get something like infinite by infinite, the total thing is undefined. So when you apply the n tends to infinite, you are not getting any specific value, but you are getting indeterminate value or undefined value. So in this case, what we can do? Anyway, we are not getting 0, right? So what we can do? I think you might have studied in your discrete mathematics course. So if such a limit value is undefined, what do you usually do that?
We can use L-Hospital rule.
Yeah, we have to apply L-Hospital rule. There is a rule called L-Hospital rule. L-Hospital rule. So what this L-Hospital rule says? That is, if you say something like limit n tends to infinite f of n by g of n means that is equal to, okay, that is equal to limit n tends to infinite f dash of n by g dash of n, right? So what is this f dash? Where is the
derivative?
Derivative, first derivative.
Start.
So first derivative, right? So that is here the f dash of n means df by dn. Df by dn, right? So this is the first derivative. So why these derivatives are playing important role? I mean, I think you have studied, right? Derivative. I think even higher secondary also it is there. Differential calculus, integral calculus, all the things. Even physics also somewhere these things are being used. The derivations are being used. What this derivation that is basically if you take y and x, right? Maybe if you take a two-dimensional plane, okay, if you take a two-dimensional plane, what happens? There are two axes, right? One is y-axis, or one is x-axis. There you are taking dy by dx, dy by dx. This is what you are saying the derivative. So if I draw a line corresponding to this dy by dx, what happens? So maybe, okay, I can draw the diagram. Here my x-axis and y-axis, this y-axis, this axis. So I have a function y in terms of x. Okay, I have a function y in terms of x. So if I plot this function, maybe I can get something like that. Maybe I can get something like that. So if I take the derivative, okay, if I take the derivative, what will I get? So if I take y as it is giving something like this, right? If I take the derivative, what I get?
So the slope of the tangent at
Slope
perpendicular.
or tangent, right? So tangent. So what we get is tangent. So I think in the trigonometry you have studied tangent, tan. So in the trigonometry sense, we say tan. Tan is sine by cos. Children, you remember that these concepts are very important. So everything you have studied in your plus 2, plus 1, plus 2, even 10th standard also. So learning something you have to associate it with wherever it is important. Otherwise, I mean, it is something like memorizing and leaving it. No use. So anyway, I cannot explain everything here. This also out of the focus. Anyway, so if I say that's a slope, as someone said, or it may be a tangent. Tangent means the line that is touching over that. Maybe tangent at that particular point. Why this tangent is important for you? Anyway, you have a function. If you plot the function, you get a curve. Why you want that? So I am talking only in terms of the engineering subject which you study. Okay, I can associate it with anything else. Even I can take physics concept and explain this. So if you are very clear in the foundation, then wherever you are linking with, that will be a clear one. So for example, I want to draw a curve. Okay, so maybe I can take something like, I want to draw a curve. So the curve is defined as a function. Curve is defined as a function. So every place it is, therefore, suppose I want to draw a curve, maybe I can talk about a computer graphics. So there I want, maybe I have a picture of a mountain. So mountain boundary is something like that. It's a uniform, something like a sine curve. Okay, it's uniform. Okay, you can define straight away. But mountain boundary, if you take that, it's not uniform, right? Sometimes the peak is there, sometimes a small curve is there, something like that. It may go like that. It may go like that. The mountain boundary. So if I want to draw that, I cannot draw just like with one function like in other cases. So what I can do is I can split this into small portions. I can split into small portions. So this is what we call as a piecewise representation. So I may have function to draw that. And with this particular piece, I can draw the curve. then next piece I can draw the curve like that. So if I draw the curve, okay, if I draw the curve like that, maybe for first piece I draw like this, and second piece I am drawing like this. Maybe I may get like this. Now what happens if I join these two? Maybe here there is a bend. It may not be smooth. It may not be smooth, right? There is a bend. It's joining. Okay, no problem, because this point, this end point and start point, corresponding x value you have taken, right? So it's joining, but the joining is not smooth. So when you draw a curve, it should be smooth, right? So what we can do? Therefore, I can take a tangent of this curve at this particular point and tangent of this curve at this point. Only the two tangent I get that. So if I make both the tangents same, then the bend, whatever the bend you got, I mean slightly you get a curve, right? So because tangent will be the same. So if I have to get a tangent, what I have to do? I have to take the first derivative of this and first derivative of this, and both the first derivative at that particular point should be same. So if I make that condition there, then the curve will be somewhat smooth. But still it is not so smooth. So what we have to go for? We have to go for the second derivative. So d square y by dx square, second derivative. So second derivative is actually called curvature. So second derivative is called curvature. So what do you mean by curvature? So for example, if I put a circle here, okay, then you should match through this. Instead of line, we are taking a circle. Okay, so if you want to get more smoother, you have to go for the second derivative. So you have to make the second derivative the point to be same. So you see, this is the, I mean, some of the places where these derivations are very important. Anyway, this is only for making you to get some interest over this topic. Okay. And you get some idea, but more detail you have to study in a later part of your course. So that time you have to keep in mind and how this is come, because the spline theory and a lot of things are there, like Bezier curve, B spline, beta spline, something like that. So there and all these things will be used. Okay. Yeah. Anyway, we can come to our point. So our point that says that whenever this limit function is some indeterminate or undefined value, then we can apply L-Hospital rule. L-Hospital rule, what it says is, instead of taking the function, we can take its corresponding derivative. We can take the corresponding derivative. Okay, anyway, I can move to the next page. Our limit function is limit n tends infinite log n by root n, right? So we can take the derivative. So limit n tends infinity. What is the derivative of log n?
So 1 by n.
1 by n. Okay, 1 by n. Then what's the derivative of root n?
1 by 2.
1 by 2?
1 by root.
1 by root.
1 by root 2. Okay, 1 by root 2. Okay, 1 by root 2. 1 by, that means n power 1 1 by 2, that is n power 1 by 2 minus 1. That is minus 1 by 2, right? Minus 1 by 2 means 1 by root 2. So we can say it is 1 by 2 root 2, right? You can say, sorry, root 10. Sorry, root 10. 1 by 2 root 10. Okay. So this is the derivative of the root 10. So now what happens? This is equal to limit n tends infinity. So this is a by b divided by c by d. So this goes to the numerator. So 2 root n by n, right? Okay. Now what happens? This root 10 and this n, we can cut and balance we can take. So limit n tends infinite. So this becomes 2 by. So if you cancel root n here and root n here means remaining is root n, right? So now when you apply n tends infinity, this is equal to 2 by 0. So 2 by infinite, 2 by infinite, because root of infinite is infinite. So any number divided by infinite, that is equal to 0. That is equal to 0. So we got the value 0. So now the property, what it says, second property, you can take the second property. So second property says that limit of f of n by g of n is equal to 0 means f of n belongs to g of n, but g of n does not belong to f of n. So we proved the statement. So sometimes if you know this property, when a problem is given, So you can make use of the property and solve the problem. So this is one example for that. Now another thing is, maybe sometimes I ask you to give example for something. Give example for something. So maybe something like I mean, you have to provide two functions f and g such that f does not belongs to R of g and g does not belongs to R of f. So sometime you can find it. Okay, you can find such functions. So f and g are the two functions. That is, one function should not be the order of something else, and the other one is also not order of this. Because previous case, one side is okay, this belongs, but the other one is does not belongs. So for that, the property we have used and we solved it. Okay, but sometimes we have to provide two functions. Both functions should not be the order of some other one. Okay. In such a case, what you have to think in? Okay, these are all you see when you give, you cannot have something studied and memorized and you should not write. But based on the property, definitions, logics, and everything what we have studied, accordingly we have to do. So when this is been given, how you can identify the function? Okay. So you see, when you say f of n is equal to r of g of n, okay, when you say f of n is equal to r of g of n, what property, what definition we have seen that. So the definition that says that there exist two constants, so one c belongs to r and n naught belongs to n, such that there is an inequality f of n less than or equal to secant g of n for all n greater than equal to n naught. For all n greater than equal to n naught. So in that, as it's asymptotic notation, we are not bothering about what happens before this n naught. All we are interested is some n we should find after that n naught. If the inequality holds, that's okay. So if you want to say that it does not belongs to, if you want to say that it does not belongs to means, what you have to say that? You have to say that you cannot find such n naught. That's all. So if it is belongs to something, okay. There it is a n naught. You can always find an n naught. Then from that n naught onwards, okay, this inequality hold. So whenever if you want to say this is not belonging to means, you have to justify that there is no such n naught exists. That is sufficient. Okay, now this is not like a proof, but what is the question? What is the question? Question is you have to give two such functions and this property to be satisfied. Okay. So one this is very simple. One example I can say is I can define even function. One of the function is even function, that is fe. So fe of x is, I am defining like that. So fe of x is equal to 1 if x is even and 0 if x is odd. Otherwise, I can say otherwise. So if it is even, value 1, if it is odd, it will be 0. I can also define another function f of x that is equal to 1 if x is odd, okay, 0 otherwise. So this is the even function, this odd function. Now I have a line, right? Natural number. Okay, natural number line. So in that, if I take even value, so I have two functions, right? Even value, this is the even value. Without loss of generality, I can assume this value is even. So when I take this even value, our this function is 1, right? But other function is 0. So your one of the function is 0 and other function is 0. Now when you take next value, this is even means next value will be odd. Next value add means this becomes 0, right? So this becomes 0 and this becomes 1, right? This value will, this is for odd curve, this is for F1 and this is for Fe. And the next value, what happened? This goes to 1 and this comes to 0. Then like that, it goes like that, right? So this is what you get. Now you see, you cannot fix n naught. Even if you fix n naught, I mean, after that also what happens? one is coming down, then another one is going up, then coming down, going up, like that. So you cannot fix n naught such that after some time one is the upper bound of something else. You cannot say that. And again, this is an example for that. Like that, you can define several examples. So the definitions are very clear. Absolutely no problem. Whatever the question it comes, you can always answer. Only thing is you have to think properly, okay, and put your view. Yeah. So anyway, 10:15. Maybe I can put one more point and stop. Okay. Then one more thing is theta notation. Okay, we can make consider the theta notation. So theta notation is satisfying the equivalence property. You see, all mathematics you have studied are coming here. Okay, so the mathematics papers is very, very important. Okay, so I think you have studied the equivalence relation also. Have you studied the relations, equivalence relation, like that? Have you studied or not equivalence?
Sir, we studied, sir.
Studied. So when you say a relation is equivalent,
If it is symmetric, transitive, and reflexive.
symmetric,
Transitive and reflexive.
reflexive. Yeah, reflexive, symmetric. A relation is reflexive, symmetric, and transitive. Then we can say equivalence, equivalent relation. So now if you say theta of f, okay. So now if you take theta notation, whether it is satisfying that the thing, that is, first it is reflexive because f can be written as theta of itself. So it's reflexive. And if you say f belongs to theta of g, that implies g belongs to theta of f because this is exact complexity, right? This is exact complexity. So whatever f belongs to theta means f belongs to theta of g means theta g belongs to theta of f. So this is symmetry. And if you say f belongs to theta of g and g belongs to theta of, then what you can say, you can also say f belongs to theta h, sorry, theta h. F belongs to theta h. So this is transitive. So this theta function satisfies reflexive, symmetric, and transitive. And again, we can say, so theta is a function. I mean, a function only that is defined over a function. Okay. So it's equivalence. This is an equivalence relation. Theta is an equivalence relation. So why we want to say, but this equivalence cannot be stated with big O or big omega. Why? Already we have seen for big O, f belongs to g, but g does not belong to f. So symmetry property automatically won't come, right? So the equivalence property can be stated only for theta notation. Okay. So if it's a theta notation, once you have equivalent relation, you can define equivalent classes. I think you might have studied equivalence classes also. So all complexity that comes into a particular thing that can be put in a one particular class. So such classification is always possible. Okay. Right. So anyway, we can stop here. Already the time is over. The next class tomorrow. So we can continue the discussion in the next class.